Hi everyone and welcome back to Analog Electronics Lectures. In this video, I'll talk about the operational amplifiers. We'll talk about the concept of the operational amplifier, introduction of the operational amplifiers, and also we'll talk about the closed loop system or the control system that is necessary to apply in an operational amplifier. The operational amplifier is a differential amplifier that has two inputs, the non-inverting input and the inverting input, and it has one output. The operational amplifier is a form of integrated circuit, IC, and this kind of amplifier is constructed by integrating a large number of electronic devices into a single semiconductor component. One of the many attractive features of the operational amplifier is that this kind of amplifier can easily configure a large number of electronic circuits, and also they can make a wide range of operations, mathematical operations. These include not only amplifiers of various forms, but also circuits with more specialized functions, such as adding, subtracting, or modifying the signal, making integration, differentiation. So we have a wide range of operations that can be made using this kind of amplifier. As we explained before, this kind of amplifier can be considered as an active electronic component. And in electrical engineering, the passive components have much better drift characteristics than the active components. Many efforts have been made to design a stable amplifier, but the temperature and power supply voltage limits encountered on phone lines, for example, cause uncontrollable gain changes. And as we said, the passive components has much better stability characteristics than active ones. Thus, if an amplifier's gain could be made dependent on passive components, the uncontrollable gain problem would be solved. One of the solutions, or one of the best solutions, is to build an amplifier that has much more gain than the application required. Then, some of the output signals were fed back to the input in such that the overall gain depends on the feedback circuit. So if you have a system like this, if we take part of the output signal and feed it back to the input in such way, where the total gain of this feedback system can be dependent on the feedback circuit. This feedback is called a negative feedback. Why? Because we feed a negative feedback from the output, and we make comparison between the input and the output. And this feedback, or this negative feedback, is underlying the operating principle for all modern-day operational amplifiers. The operational amplifier, as we said, has two inputs, the non-inverting input and the inverting input, and one output. The gain of this amplifier is usually large or huge. What's the problem of this gain? It's large. When we have high gain, any small change on the input will cause large change on the output, and that causes instability. So that's why we need passive element. This passive element can hold the signal and take feedback from the output. We need control system here to take feedback from the output, take some of the output voltage or output power, and make some adjustment and give back to the input. This feedback can be done or can be achieved using passive elements. As we said, the passive element has much better drift characteristics, and they can hold the signal much better than the active elements. So these passive elements can hold the fast change in the signal and make more stable operation for the amplifier. The combination of the active components that can build high gain and the passive components that provide better controllability features enable us to design the required gain of the amplifier with more stable operation. Let's talk briefly about the feedback system. In the feedback system, usually we have the forward path, which is the system or the amplifier that we have. And this forward path has a gain, a specific gain, which is A. Usually this forward path has an output. Let's call that this output is X out. Now, if we want to take feedback from this output, so we measure the output signal and give it back to a certain system, a feedback system. This feedback system can be sensor, can be anything, and give the value back to the input to make comparison. Let's say that this feedback system has a gain of B. So what is called this feedback gain. And we return back this signal to the input to make some comparison. When we make comparison between the input and the output, we know the error or the desired value that we need and supply the system again. So this is the general behavior of any control system or any feedback control system. Usually this input is, let's call this X input, and here the feedback system, negative feedback system, and here we have the subtractor. Now, if we try to calculate these values, now here we have output x naught, input x input xi. We have the gain A and the gain B for the feedback. Okay, if you look at this point here, so this point is equal to how much with respect to x out? This should be x out over A. Why? Because x out over A times A is equal to x out. Now, if you look at this point here, this should be B times x out because we have feedback here, B times the value of the output signal. Let's find the equation or the relation, try to find the relation between the input and the output. So x out over A, this value, is equal to how much? From the subtractor here, the input value, which is x input, minus B times x output. Now let's do some arrangements here. So we can say that x naught over A plus B times x naught is equal to x input. Take x naught all together. So this 1 over A plus B is equal to x input. Finally, we can get this equation or this relation x out over x in. This will be equal to A over 1 plus A times B. And this is what we call the transfer function, which is the relation between the input and the output. The relation between the input and the output is what? Is the closed loop gain. And here A is the open loop gain. And B is the feedback gain only. But the closed loop gain, output over the input, is equal to how much? A over 1 plus A times B. So the overall gain, which is the closed loop gain, G, is equal to x naught over x input, which is A over 1 plus A times B. And A in this case is known as the open loop gain because we have no feedback. If we remove all the feedback, the open loop gain is A. And G, which is x naught over x input, is the closed loop gain. Now let's study the effect of the product A times B. Again, A times the feedback gain B. Now, if this A times B is negative and less than 1, so at this case, 1 plus A times B should be also less than 1. In this situation, the overall gain will be larger than the open loop gain, and we have positive feedback. If this value, the A times B, is positive, then 1 plus A times B will be also larger than 1, because any value plus 1 is larger than 1, right? So in this situation, the gain, the overall gain, will be less than A, and we have negative feedback at this moment. Now, if this AB is positive and way larger than 1, so what's happening here? So G, which is A over 1 plus A times B, if this value much larger than 1, then the whole value here should be almost equal to A times B. As if we said like infinity plus 1 is equal to infinity. So, or 1000 plus 1 is 1001. So we can say this approximately same. And here A will go with A. So this will be 1 over B. Now, finally, the gain, the overall gain for the closed loop system depends largely on the feedback gain. So this is the conclusion now. This gain is independent of the gain of the forward path. So it doesn't matter what gain we have in the forward path, no problems. The most effective gain will be the feedback gain, this value. Coming back to the operational amplifier, as we said, this amplifier has non-inverting, inverting input. We have output, and also we have the voltage source, positive and negative. So let's make some terminology here. So V plus is the non-inverting input. V minus is the inverting input. And these are actually the signals that we are hoping to magnify or amplify within the amplifier. And this is the output. That is the amplified signal. And here, V plus and V minus, these are just the external power source, the positive and the negative power supply. And these values can be like in the range of plus 15 volt, minus 15 volt. And conventionally, the power supply connections are not shown in the circuit diagram. We just show this diagram, the operation amplifier with the two inputs and the output. And these only in the practical circuit. We connect this to supply the op-amps. The ideal operational amplifier will be similar to the differential operational amplifier. And the characteristics of this amplifier is what? The voltage gain is infinity, very large, and the input resistance is infinity as well, and the output impedance is 0. So this is the ideal operational amplifier. If you try to draw the equivalent circuit of that amplifier, we can easily say, here we have the controlled voltage source, we have the output, V out, and here we have an open circuit, because the input impedance is infinity, and this is V in, and this is V plus, V minus. And here the controlled voltage source is equal to how much? AV times V input. Or we can say this is AV times V plus minus V minus. And this is the equivalent circuit of an operational amplifier. Next lecture, we'll talk in details about the operational amplifier rules and configurations, and see what are the specific circuits or what are the specific rules that we can apply within the operational amplifier, and what kind of circuits that we can build in order to achieve some operations, for example, or to achieve like subtraction, addition, amplification. We'll see the inverting amplifier, the non-inverting amplifier, and many other circuits that can be built using the operational amplifier. So see you next time.